It's going to be life on other planets. We'll start off with the Earth, life on our solar system. We're going to then do a search for the exoplanets, and then I'm going to try to say what counts for life when you're looking for life on other planets. Now, different types of life on our planet, Earth. I'll go through a few of them. A study has turned up a life form that's as deep as 1,600 feet below the ocean floor and even below land up to 2.7 miles with no sunlight. Energy is sparse and must be harvested from the surrounding materials and their chemical reactions: hydrogen, methane, sulfate, serpentination, and the dead or living bodies of neighboring microbes, and even radioactivity. Some cells in the deep biosphere divide only once every 1,000 years. So we've got a couple types of life that do this. There are chemosynthesis instead of photosynthesis, using sunlight to create energy. These organisms rely on chemical synthesis. This process uses chemical reactions to produce energy. The key players are bacteria and archaea, are primary organisms performing this. They oxidize inorganic compounds like hydrogen sulfide, methane to obtain energy. And that's where you see the deep sea vents. Those are the barophiles. The other ones are the thermophiles, which have developed special proteins that allow them to tolerate a broad range of temperatures. Some even require a temperature of around 140 degrees Fahrenheit to exist at all. And then there's another ones that develop sponges that thrive on oil. And then there's some that have to have cold sections, and even sunken wood develops into habitats for microorganisms. So genomic analysts of microbes from the Canadian Arctic provide insight into the life forms that can survive on Mars. The Lost Hammer Spring in Nunavut in Canada's high Arctic is one of the saltiest and coldest terrestrial spring discovered to date. The water, which travels up through 2,000 feet of permafrost to the surface, is extremely salty at around 25%, and perennially at sub-zero temperatures at a negative 23 degrees Fahrenheit, and contain almost no oxygen, one per million dissolved oxygen. The microbes found and described at the Lost Hammer are surprising because, unlike other organisms, they don't depend on organic material or oxygen to live. Instead, they survive by eating and breathing simple inorganic compounds such as methane, sulfates, sulfides, carbon monoxide, and carbon dioxide, all of which, by the way, are found on Mars. And speaking of Mars, they're pretty sure with all these probes that we have sent up there that Mars was once covered by a vast ocean. Now, most of it escaped because it didn't have the atmosphere to keep the oceans. So they're trying to figure out if was once life on Mars. And what they've come up with is these beads, if you can see them, these little tiny beads. And they're called leopard spots. And a close-up of Mars rock nicknamed Chivaya Falls shows the distinct spots. These leopard spots are related to chemical reactions known on Earth to fuel life and are often associated with the presence of microbes. So they believe that those little dots are actually microbes, but they can't prove it. So they still don't know if it's true. So the way it happened was early Mars was a molten mass. Then they had the ocean, and the ocean disappeared, and that's where these not zebra spots, leopard spots came in. So these are kaolite minerals are what's left behind a rock after it's been in flowing water for eons. Over time, the water leaches away all of the elements except for those that are really insoluble, leaving behind what is found on Mars. It's fascinating. It is unexpected on a cold, dry planet like Mars. On Earth, these minerals form where there is an intense rainfall and a warm climate. In hydrothermal systems such as hot springs, both environments are ideal conditions for life as we know it. And so basically what they did is they found these minerals called kaolinite on Mars, and the only place they could have came from was water. So if you've ever looked at Mars, you'll see that it has all the spots where water used to be in the way of rivers, streams and lakes, and oceans. Now, they're trying to reach Jupiter in 2031 with the Europa Clipper. And whether the moons could harbor life is unknown, but it's on the list of possible places NASA would like to look. Now, not only does it probably have salty oceans, but a layer of rock more than 150 feet beneath the surface. So there's 150 miles rather of ocean, and both the have are key conditions for leading what's to life. So you've got the minerals in the rock that's below it, and you've got the ocean. The ocean, oxygen and hydrogen have also been detected from Callisto's extreme thin atmosphere, and that's what it looks like. Now, Jupiter's moon Europa, uh, in a in April 2030, setting up close to 49 flybys of the frigid moon Europa. Data from previous missions and long-range studies from Earth indicate a vast salty ocean lurks behind the moon's frozen crust, providing a possible habitat for habitable environment. Whether the microbe life exists in the oceans is unknown, but Europa's Clippers instrument will try to find out if it's at least possible. Uh, the Titan is will be they're going to send that back to Saturn, and they've already sent the Hygiene's probe. I think it was 4 or 5 years ago, and what they found was that they have these lakes of ethane and methane. It's too bad we couldn't get them down here and use for our energy. But science believe that these could host prebiotic chemicals, making it a key destination for studying the origins of life and the progression of prebiotic chemistry. And that's what the probe will look like. It's about the size of a small bus. Now, here's something you want to think of. As you'll see, that's what our cosmos looks like. But Earth is just one of 3.2 trillion planets in our galaxy. Now, that's one galaxy. The sun is just one of 200 billion stars in the Milky Way. The Milky Way is just one of 2 trillion galaxies in the observable universe. So when you think about it, mathematically, it's almost be impossible that there couldn't be some form of life on another planet or in some other type of location in with all these possibilities for life forming. So the history of exoplanets, by the way, exoplanet is anything outside of our galaxy, discoveries. In 1917, the first possible evidence of an exoplanet was noted, but was not recognized as such. In 1992, the first confirmed detection of an exoplanet around a pulsar. These were the first exoplanets discovered and orbiting a pulsar, which was a rapidly rotating neutron star. In 1995, around a main sequence star, the first confirmed exoplanet orbited a main sequence star like our sun. As of December 19, 2024, there were 5,811 confirmed exoplanets in 4,340 planetary systems, with 973 systems having more than one planet. Now, this is cool. I love this thing. It's an exoplanet and catalog that NASA puts out. And as you can see, you've got quite a different ways you can go into it with news, resources, exoplanet overview, but it shows the planets. And what you can do is pick them out by terrestrial, super Earths, Neptune-like gas giants. And then it gives you a catalog of every planet. So if we take one, we can look into it and it'll show you a picture of what they think the planet looks like. And then it'll show you where the system is and what it looks like. And then it'll show you what they think the star looks like. So it's an M type type of star, which is the most common type of star, which is much redder and cooler and dimmer than the sun. But I believe that it's also M type sun is also our sun. So then it gives you some more information about it, and it tells you the planet radius, which is 0.61 size of the Earth. The planet type, it's terrestrial. The method is that they found it was transit. Its planet mass is eight Earths. It was discovered in 2013. It has an orbital radius of zero point 0.5 and an orbital period of 0.2 days. So it's going pretty fast around that sun. Let me go back. And as you'll notice, there's a whole bunch of them that you can go through, all the way up to 391 pages of them. Okay, so what do scientists think about this? Perhaps it's not actually surprising, but a strong consensus. Perhaps it is surprisingly weak. Perhaps what? Perhaps it's not actually a surprising strong sensitive. Perhaps it's a surprising weak consensus, considering the numbers. There are more than, like I said, 100 billion galaxies, and we know that habitable environments are everywhere. Let's say that there are 100 billion habitable worlds, planets, or moons in the universe. Suppose that such pessimists that we think of life's chances of getting started in any one of them habitat world is 1 billion in a billion. In that case, we would still have to agree to the statement that it is likely that there are alien life on exist in the universe. And this is a breakdown by physics, biology, non-astral biologists, and astrobiologists. And as you'll see, they all pretty much strongly agree that there is life. But if you look at the bottom part, um, the intelligent life is only about a third or fourth of they believe, but there's complex life and life itself, which I think is probably most possible, which is microbes. How do we find and classify them? So one way is transits, which means that when the planet goes in front of the sun, there's a dip in the light, and from that they can figure it out. And how do we use spectroscopy? Another way is by just looking at them. Then there's something called gravitational microlensing, and that has to do with the fact that when the light from a background star passes just behind it, what that means is when a planet goes in front of the sun, it causes the sun to actually wobble back and forth as it's going back and forth. And from that, they can tell that the radial velocity, which is how fast it squeezes and stars closer away, those cause gravitational tugs in that way from orbiting. It has to be from orbiting planets. The transit is just when the planet goes in front of the sun and it disappears. Not disappears, it causes the light rays from the sun to go down, and they can do a lot of different things from that. So then there's spectroscopy, which I'll explain later, and then there's the James Webb Telescope can actually uh, do a lot of things by looking directly at the sun. And then there's gravitational microlensing, which means that the light from the background of a star behind it, the planet in orbit, the star will appear properly positioned for the telescope as a spike in light intensifies and the background star goes by. The planet will appear as a secondary smaller spike. And from that, they can tell a lot of different things. And then there's the direct imaging of the planets. Okay, so what's the maximum distance we can detect civilization? The earliest radio waves, such as the first broadcasts of a radio wave in the 19th century and 20th centuries, have been traveling through space for over 120 years. Since radio waves travel at the speed of light, approximately 186 miles per second, they would have reached a distance of roughly 120 light years from Earth. So they're now watching I Love Lucy on radio. The SETI Institute, which is us trying to find these radio waves, is a nonprofit organization dedicated to SETI research, founded by an astronomer and science communicator, Jill Tarter. That was around for 5 or 6 years, and then NASA started a program, but it only lasted a year because they couldn't get the funding. Now, the only thing that the NASA program found was something called the WOW signal, WOW, but it's kind of been discredited because they couldn't see it again, and they believe it might have been due through a fault. So to put it in perspective, that's how a tiny fraction of the Milky Way's galaxy, which spans approximately 100,000 light years across. These waves are essentially forming a faint expanding bubble around the Earth, increasing any civilization within 120 light years radius with the right technology could, in theory, detect those signals, though they would be incredibly weak by now due to dispersion and other cosmic inferences. So what that basically means, if they had the right radio on some of these planets, they'd be able to pick up our first radio signals, and somewhere along the line, they'd be able to pick up our TV signals. Now, here is just a breakdown of how far these things have gone. The AU, by the way, an AU is an astronomical unit, which is about the distance from the sun to the Earth. So as you can see, these radio case ones, which is planetary radar, are going out to 10 billion, distance of 10 billion of these AUs. And it goes all the way down to objects on the Earth, which is just basically, you can see them from not too far from the Earth's surface, and everything in between. For example, lasers are at 10 to the third AUs. So let's skip that. And here's the first picture of a planet that was taken back in 2004 by the Very Large Telescope at European Southern Observatory in Chile. And they've taken quite a few since that time. Now, this thing tells you the relative density of planets. And what they did is they put it on a graph. On the top is planet radius in Earth radii. So one is one Earth radii, as you see the Earth pointed out in red, and then 2 and 4. And this tells you that there's a possibility, there are 1,000 exoplanets in this diagram. And as you can see, most of these are all falling within what's called the Goldilocks zones, which I'll explain in a little bit. And on the left-hand side, it tells you how fast these planets are going around the sun in days. And as you'll notice, it goes all the way down to 1 to over 300, which is where we're at, with a bunch of them being from 3 to maybe 30 days. So those are all possibilities of planets being and the TRAPPIST System 1, which is one that I'll be talking about a little later, you'll notice is traveling at about 1.5 times around its sun. So they're going pretty fast, which I've never been able to understand. So what is these things? Here's the main process used for finding exoplanets. Radial velocity method, Doppler spectrography. As a planet orbits its star, it exerts a slight gravitational pull on the star, causing it to wobble back and forth. This wobbling motion slightly shifts from the starlight, which can be detected by observing changes in the star's spectral lines, the colors that it emits. The transit method is basically when it goes in front of the star and causes it to darken for a little bit. Microlensing is when a star planet passes in front of a more distant star. The gravity of the closer star bends the light of more distant star and magnifies it. If the planet is present, it causes a brief additional magnification of light. And direct imaging, of course, is when daily observing the planet's faint light, usually by blocking out the much brighter light of the star using advanced techniques and powerful telescopes. And then there's astronomy, which measures tiny wobbles of a star caused by the gravitational pull of the planet. So they can actually, the planets are pulling on the sun and causing it to wobble. And this is just I thought it was a pretty good view of what's happening. You'll see the blue, which is the planet going around the sun, and every time it does, the thing shows the spectrograph on the bottom, and the spectrograph, which tells you what chemicals are taking place. And this is pretty interesting. I'll see if I can get this. This is going to be a short 3-minute thing that'll explain what I'm trying to explain to you a lot better.
Since the early 1990s, astronomers have known that extrasolar planets, or exoplanets, orbit stars light years beyond our own solar system. Because most exoplanets are too far away to be directly imaged, characteristics such as size, composition, and atmospheric makeup must be determined through a variety of indirect methods. For instance, when an exoplanet passes in front of its star, or transits, it blocks a fraction of the star's light and causes a dip in brightness. Large planets block more light, so the size of the dip can be used to determine the size of the planet. By observing an exoplanet's gravitational pull on its star, astronomers can also determine the planet's mass, and thus calculate its density to see if it is composed of rock, like Earth, or gas, like Saturn. But to fully understand an exoplanet, astronomers must study its atmosphere, and the information that they need is encoded during a transit. As the planet crosses its star, its atmosphere absorbs certain wavelengths of light, or colors, while allowing other wavelengths to pass through. Because each molecule absorbs distinct wavelengths, astronomers spread the star's light into its spectrum of colors to see which wavelengths have been absorbed. The dark absorption bands act as molecular fingerprints, revealing the atmosphere's chemical makeup. Knowing the depth and density of the atmosphere is also important. To figure this out, astronomers observe the transit at many different wavelengths. At wavelengths where more absorption occurs, the planet will appear larger, with the change in size indicating how deeply the atmosphere extends, and its density at different altitudes. Measuring the depth of absorption at each wavelength gives astronomers the planet's transit depth curve, which allows them to model the composition, height, and density of the atmosphere, providing a detailed picture of the planet. Recent studies suggest that exoplanets and their atmospheres come in a wide variety. At one extreme are hot Jupiters like WASP-19b, a boiling gas giant that orbits its star far closer than Mercury orbits our Sun. Visitors who could survive the heat might complain about the air quality. Planet WASP-19b's jagged transit depth curve suggests a deep atmosphere of poisonous hydrocarbons, with methane and hydrogen cyanide far more abundant than water. By contrast, planet Gliese 1214b is a comparatively inviting water world. Its nearly flat transit depth curve hints at a shallow atmosphere of pure steam, enveloping an ocean thousands of kilometers deep, with an interior of hot ice, water solidified by extreme pressure rather than cold. As detection methods improve, astronomers will search the atmospheres of Earth-sized planets for signs of life such as water vapor, oxygen, and methane, taking us one step closer to finding a world like our own, all thanks to some flickering starlight.
So that's basically how they detect it, and I think that's a pretty good explanation of how the spectrum works. So I'm not going to go through this all, but there's satellites that are looking for life on planets. The Ariel will survey about 1,000 known exoplanets from gas giants to rocky super-Earths. Cheops, which was launched in 2019, will measure planets' sizes. And TESS, which is the new one, it's already identified over 7,000 exoplanets with more than 400 confirmed so far. So there's probably, I'm guessing, about 13 of these satellites that are looking for planets, and I'm guessing there's probably another 20 or 25 studies which are trying to figure out if there is life on other planets. The sad part is NASA's budget, based on what's going on in our government, has been cut in half. So they believe that most of these they're going to stop funding those. However, the James Webb Telescope will be funded, and maybe a couple of the other ones, but it's just going by the wayside. This one was interesting. The Pandora and the Sphere X are going to study 20 planets for 1 year time, and they're going to be doing all kinds of testing on it. So that should give us a lot of things. I hope they make it before the funding stops. Kepler, I'll skip that one. Okay, there's something called the Fermi paradoxes. Where is everybody? The paradox arises from the vastness of the universe and the seemingly high probability of life arising elsewhere. contrasted with the complex lack of evidence of contact with extraterrestrial civilizations. The vastness of the universe is incredibly huge, containing billions of galaxies, each with a billion of stars, many of which have planets. The habitable planets it's reasonable to assume that a significant fraction of these planets are in the habitable zone around their stars, where conditions might be right for liquid water. Life's emergence, even if the probability of life arises at a given planet's small and sheer number of planets, make it seem likely that if life has arisen many times throughout the universe history and the evolution of technology, given enough time, some of these life forms might evolve into intelligent, technologically advanced civilizations capable of interstellar travel. Where are they? If such civilizations exist, even if they travel at a fraction of the speed of light, they should have ample time to explore and even colonize. Now, one of the problems I have with if there are these advanced civilizations and they saw what we're up to, would they really want to come here? So, what is a complexity of life? Complexity of life refers to the intricate, interconnected, and often unpredictable behavior of living systems, ranging from a single cell to an ecosystem and societies. It arises from interplay of many components, genes, organisms, individuals, followed by simple rules, leading to emergent properties that cannot be fully predicted from the parts alone. And the key concepts is emergence. A complex system exhibits behaviors or patterns. Consciousness, flocking, and birds is an example that emerge from interactions among simpler components, and it's not reducible to the individual parts. Nonlinearity, small changes in inputs, mutations can lead to disproportionate effects. The evolutionary leaps that we took, for example, unlike linear systems where output scales predictably. Self-organization, life tends to form orderly structures without external direction, like ant colonies or cellular structures, driven by internal rules and feedback loops. And adaptability, living systems have evolved to handle uncertainty, balance and stability, robustness and flexibility, adaptation through mechanisms like natural selections or learning. Interconnectedness, components in living systems are deeply linked, forming networks, food webs, neural networks where changes in one particular ripple across the whole. So what do we need for a simple life? First thing you need is water. It's essential because many biological processes, it acts as a solvent, transports nutrients and helps regulate temperature. Carbon, you'll need carbon because carbon is a backbone of organic molecules forming the building blocks of life like proteins, carbohydrates, and lipids. Nitrogen, a key component of amino acids, the building blocks of proteins and nucleic acids such as DNA and RNA. Phosphorus, which is essential for forming of DNA and RNA as well as cell membranes, and sulfur, found in some amino acids, plays a crucial role in many metabolic processes. Now, I'm sure you've seen Drake's equation at one time, and this guy Drake in 1959 tried to figure out how many possible civilizations that are in it. I'm just going to go over it quickly so that you can see it. The number of technologically advanced civilization in the Milky Way, which is N, equals R, which is the rate of formation of stars in the galaxy, and FP sub P, which is a fraction of those stars with planetary systems, and that's times the number of planets per solar systems with environments suitable for life, times the FE, which is the fraction of suitable planets on which life actually appears, and times Fi, which is the fraction of life-bearing planets on which intelligent life emerges. And then you got FC, which is a fraction of civilization that develops a technological that release detectable signs of their existence into space, and times L, which would be the length of time such civilizations exist. So I can go it. Now, I talked about the Goldilocks zone, and what that means is they figured out that in order for water to be liquid and for it be able to mix with the chemicals of life, it has to be a certain distance from the sun, depending on the size of the sun. For us, with the sun, it'd be between a little past Venus and before Jupiter. So Mars is included in it. And then past that, the water probably wouldn't be liquid. An old sun would have it could be closer, and duration of planet in the habitable zone can stay warm for about a half a billion years. Now, a spectrum of planets obtained with the Webb near infrared microscope and slitless spectroscopy on the near infrared spectrum displays an abundance of methane and carbon dioxide in an exoplanet's atmosphere, as well as possible detection of a molecule called dimethyl sulfide, DMS. When plankton dies or throughout other biological processes, they release DMS into the atmosphere. And as you'll notice, this planet that they found actually has this DMS sulfide, so they believe that that may be some form of life, although they can't be sure. Now, we were talking about our possibilities. When you think about it, we've been around for the estimated age of the user is 10 billion years. The number of years humans have been civilized have been around 200,000. Dinosaurs were around on Earth for 165 million years, and we've just been around for 200,000. That gives you some idea of how we screw things up. Evidence such as microbe life existed on Earth very early in its history, potentially as far back as 3.7 to 4.28 billion years. Now, as you'll notice, we've only been able to look back maybe around 100 years to even think about finding other forms of life. So it's a very short distance so far. In October, a diverse group of scientists gathered, I think, outside the box on evolution. They wanted to step back and explore sort of processes to create order in the universe, biological or not, to figure out how study of emergence of life, totally unlike life on Earth. Two researchers argued the complex system of chemicals and minerals when environments that allow some configurations to persist better than others and to evolve to store larger amounts of information. As time goes by, the systems will grow more diverse and complex, gaining function needed for survival through a kind of natural suggestion. Now, I wanted to show a movie on this, but it was too long. And what this is, a scientist got oil droplets and he put them in a system, and the oil droplets started to do stuff like circle around each other, try to find food, and stuff like that, which I thought was really interesting. And that's what got me on this and talked to John about doing something like that. But like I said, it's just too long. Where there may be possibilities of life on other planets, which I think is probably a thing that's happening, is the two would be bacteria and viruses. And because they seem to cooperate, they have a better way forward. They organize into cells and role in the community, specifically their metabolism. Okay. So what I'm getting at is these things form communities, and they keep creating more of their either bacteria or viruses. And that is what I think is possible for life. And they're everywhere. Living microbes have been found sealed within the fracture of a 2 billion-year-old rock dug up from the Bushveld indigenous complex in South Africa. And when you think about it, the ratio of microbes to human cells in the body is 10 to 1. So there's more microbes than there are human cells. And that is approximately 3 pounds of microbes in each one of us. So beyond the elements, what else are they looking for? Sunlight, which is photosynthesis in plants, or chemical energy from hydrothermal vents or other geological sources, and a stable environment, protection from harmful radiation rather. So that's a big problem. Our atmosphere does that for us by stopping most of the radiation coming, and a relatively stable temperature range. I think I'm going to skip this one. And this Clavister scale, he figures that there's three types of planets, three types of planetary civilizations. Type 1 is a planetary civilization, which is a civilization that can harness all the energy available on the planet. We are not yet a Type 1 civilization, although we are getting close. A Type 2 civilization is that can harness the energy of its star. This might involve something like a Dyson sphere, and a hypothetical structure that completely surrounds the star. And type 3 is a galactic civilization. That's where they are going out and harnessing other planets and other means of going. So the first experiment that they did to see if they could create life was the Miller-Urey experiment. And what he did was put lacking oxygen and composed of methane, ammonia, hydrogen, and water. And then they subject this to electrical discharges simulating lightning and heat. The results of the products were analyzed, and the result experiments successfully produced a variety of simple organic compounds, including amino acids, the building blocks of proteins, and other organic compounds such as aldehydes and carbolic acid and hydrogen cyanide. So that's basically what it looked like. And I forget how many years that they did this, and it may even still be going. And this was back in 1952. So it performs like a black sludge that they believe is what produced us, as a matter of fact. Now, they used to think that it came from lightning, but the theory proposed that tiny sparks called microlightning generate between charged water droplets could have provided the energy needed to create molecules essential for life from simpler inorganic materials. These molecules include amino acids, the building blocks of proteins, hydrogen cyanide, and uracil, a building block of RNA. These reactions would occur in the early Earth atmosphere, which is thought to have been rich in gases like nitrogen, methane, and carbon dioxide and ammonia. So the reason they believe this is because a lightning strike usually destroys anything, or if you have these micro lightnings, it could possibly form different types of reactions. The building blocks of life form of space dust, offering clues to the origin of life. And what this is basically is they think that particles in space have the all life on our planet relies on proteins. This raises the possibility of building blocks of life that didn't emerge on Earth at all, but were seeded from here in outer space. The authors propose that cosmic molecules as a source for these first peptides and possibility the seeding of Earth's first life. Carbon-rich meteorites and some of the most chemically primitive materials can study. They contain water, organic molecules, and even ammonia acid. So what they're getting at is they think these things came from space, and the micro lightning helped to get it started. And here is they when they went to the asteroid Bennu, they found amino acids and other ingredients for life, and that's where this arrow is. They actually took a picture of this thing on these components, which might have been existed on an asteroid. Phosphorus can help make sugars. Clays can help to bring things like nucleotides that build RNA and DNA. Sodium brine are essential for both, speeding up those reactions and help release of these molecules. So some people think that the life was started from different types of things coming from space. And panspermia is this is a good one. This is a thought that life on Earth was actually came from other civilizations, that Earth life might have started with microbes sent to the protected payload, pointing to the complexity of early genetic code, meaning that somebody sent these things to try and farm us or terraform us into things. And there's been a few scientific movies that have gone this route. The building blocks of life, as you know, is protein, amino acids. The human body has over 100 different proteins forming many different functions. The human body utilizes 20 different amino acids to create thousands of proteins it needed for function. And we knew that. So the one thing that they're very excited about is this TRAPPIST-1 planets. And as you can see, the planets fall into where our planets are pretty close. So they've been studying these things in the last couple of years, and they believe that it might be a place where they'll find life. And Bernard's star, a red dwarf, they just found a common. Importantly, red dwarfs are cooler and more massive stars, meaning they can host larger habitable zones, regions within the solar system that are temperate enough for worlds to harbor liquid water. close to themselves where the planets often form. Scientists are also using the James Webb Space Telescope to discern if such rocky worlds are round red dwarfs could host atmospheres like Venus or Earth. To find these worlds, use something called radial velocity technique, which wherein a specialized high-resolution instrument called the Maroon X was mounted on a 26-foot telescope in Chile. Is the sun where it's close looks for stars exhibiting extreme wobbles. Recognizing life, we look at two main questions. She said, first, what conditions in chemistry are needed to sustain life? And we find those conditions should expect life to respond the same way it did on Earth, or it take a completely, entirely different paths. Another question is, if it necessarily condition is met, does life always emerge, or is it something else we're missing? So we're almost done. Besides the things that I've been talking about this whole time, there might be lives out there that, for example, is pure energy. It never got into the matter form. Transformation, meaning that it transformed from some other systems. And the one that we're all worried about now is AI. Maybe AI is a life form out there that just kind of took over the humans or creatures that created it. We tend to think that what if life exists elsewhere? It follows the same evolutionary path that it did here on Earth, but that may not be true because the evolution of life elsewhere may have followed a very different pathways from that on Earth. Living habitats could also exist outside traditional habitat environments around other stars where they have would have an unusual but potentially detectable biosphere. And John and I were just talking about that. We was talking about on Jupiter the in order for a life form to exist, it'd have to be 100 times the size of us because of the gravity. But there was a theory going out that if a life form could float in the clouds of Jupiter, it might be some type of light form. And this was interesting, and I found it. Nick Herbert has argued for quantum animism, in which the mind permeates the world at every level. The quantum consciousness assumption, which amounts to a kind of quantum animism, likewise asserts that consciousness is an integral part of the physical world, not an emergent property of a special biological or computational system. Since everything in the world is at some level quantum systems, this assumes that there requires that everything to be conscious at that level. If the world is truly quantum animated, then there is an immense amount of invisible and interior experience going around all around us, and that is presently inaccessible to humans because of our own inner lives are imprisoned inside a small quantum system located deep within the meat of the animal brain. Werner Krisling wrote regarding this quantum animism, Herbert's quantum animism is different from traditional animism, in which it avoids assuming that dual model of mind and matter. Traditional dualism, that some kind of spirit inhabits the body and makes it move, a ghost in the machine. Herbert's quantum animism presents the idea that every natural system has an interior life and a conscious center from which it directs and observes its actions. So basically what they're saying is we think that we're the only things around experiencing life, but there may be everything. He believes that everything has some type of system going on. So with that, we can go to questions.
Thank you, John. Bill Tittle, you have your hand raised. Bill, you have to unmute. Bill, you have to unmute.
I got it. Couldn't get the screen up. John, that was just a fabulous presentation. Thank you very much. So much to digest, but I guess what I take away is I'm convinced that there's life out there, and I have two reactions. One is it scares the shit out of me because look what we did when we were the New World, and Columbus went over. He killed all the Indians, and so that worries me. And the other thing is, it may be just so far away that we'll never interact. But I think it's really important that this isn't a question, this is just reaction, that human beings explore the universe, because in another 100 years, this place is going to be a dump. So we got to go somewhere else. It's sort of the Elon Musk, but good luck with getting the NASA budget increased. Do you have any reaction to that?
Well, I agree with you with the budget. I mean, I cannot believe that they put up these satellites and they're just saying, "Oh well, we don't need them. We're gonna not research," which is sad. But I have a friend who's going to Mount Sinai, and she was in an experiment with some research on medical stuff, and she was talking to the person who was handling her, and he said that 80% of the research that Mount Sinai's was doing is stopped right now because they don't know if they're going to have the funding and they don't want to have to pay people. So, yeah, it's bad that we can't find out if there's life on other planets, but we might be screwing with the planets around here.
Okay, Mark Edelman.
Yeah. Well, this was such a stimulating presentation. There's so much in it. Thank you for that. But something that wasn't in it was the idea that in order to have life, you pretty much have to have reproduction and selection. And everything you said is consistent with that. You need selection so that the most successful combinations, are the things that survive. And so you get selection for free because other things don't survive. And then you need reproduction so that life can evolve. And the theory behind that is that the only way to get high complexity and to have many capabilities, which life has, is if you get it gradually. You can't get it all at once. You have to get it gradually, step by step. And that is reproduction and selection creating evolution. So I just wanted to put that in as an add-on to what you discussed.
Yeah, thank you, Mark. Like I said, I only had he only gave me an hour to discuss all that, so that would have been a very important thing that I kind of skipped over. Bob Deller has a question.
Yeah, there's a lot of stuff in there. You went through it very quickly, and it was hard to absorb everything. But what struck me, and it really stood out to me, was the quote by Nick Herbert. And I think that, Mark, what you just said is an example of what he's talking about. There are our brains and our knowledge of the ultimate universe are so minuscule that we are unable to think beyond what we know. And there's an assumption that there may be a natural selection, that there may be incremental advances, because that's what we know. But I think it's thinking about what we don't know, which is the most important thing when venturing in to the exoplanets, because there's no reason at all why there may be life that's similar to us. To me, it's much more likely that there's life out there that's not similar to us. And that's not based on the chemicals that form life here in our world. And there are other ways that life is formed that we have no comprehension of. So I just raise that because we just don't know. I mean, I used to think when I was a kid that ants were from outer space, because they were there. They had a system. They had a leader. I mean, Who knows? Maybe they were the invaders, or what about the mysterious circles in wheat fields that have been made that nobody could explain? Or if you go to uh, Mexico with the Mayans, what they were doing back in their time was inexplicable. It was beyond anything that anybody could comprehend. And as a matter of fact, I mean, think about this. If you stand there, I think it's I always get the name wrong. I say Machu Picchu. I know that that's the wrong word, but if you stand there and clap your hands once, the sound is repeated 7 times anywhere. So how was that done back then? So I just, because I'm interested in all this, and I just think that a, we are less than a speck of sand in the trillions and trillions of entities or universes or planets that are out there, and there's no reason to believe that there are not life generating planets that generate life in a completely different way that we have no concept of whatsoever.
Well, you're right about that, Bob, because if you think about it, uh, we've been studying consciousness and how that forms, and we still have no idea what consciousness is. So yeah, we could be in this conscious world, but there could be a whole world that surrounds that we don't even know about. Maybe we're just like a TV for some advanced
Yeah,
civilization, and they enjoy our life because they don't have bodies anymore.
hey, yeah, maybe we're the Matrix. Maybe we're in the
Matrix.
Matrix. Who knows?
Uh, Tom, I guess you're next.
Unpaid.
Bob stole my point, really. We always talk about life requiring water to exist. And my question is, with all of the possible universes that are out there and planets, why can't there be completely uh, other systems in which life forms?
You're absolutely right, Tom. I mean, I think that's what we're all talking about, is that we're just too used to life on Earth. And for all we know, the ants may be looking at us and saying, who are these gods? Walter, I guess you're next.
I thought Alejo was next.
Okay, Al.
Well, I'm happy to go. John, thank you for a fabulous talk. It's one of the best talks on life I've heard. Um, I have a lower bound question. What is the quickest time in which life can emerge? Are there any theories on that?
I'll have to ask Alexa that. um, well, the interesting thing, and what John had asked for people to put together a show, and so I sent him that thing about the oil, which is a 10-minute discussion of this guy who took oil droplets and basically created a form of life that was, number one, looking for food, looking for rather energy, and associating with other forms of these oil droplets that he had. I mean, I found that just amazing, and that started me to think, well, maybe there is different processes out there that we're just not familiar with, because we're so stuck in our brains and our consciousness that we don't even see stuff. I mean, like I said, for all we know, there may be this whole energy fields that are all around us, and they're presenting us with this nice life that we have for a very short period of time, and that's what we're in, and that's what we're kind of stuck with. Why we can't explain consciousness just amazes me. So I don't know if that answered your question, but
Well, I liked your definition of quantum life, by the way.
I'll have John send that out, because when I read that quite a few years ago, I keep bringing it up just so it keeps reminding me of that. If John might do that for me.
All right. Walter?
Yeah. Okay. Back in the 2000s, I knew somebody from Bell Labs that claimed that global warming was a hoax. And he said the ice caps on Mars were melting just as quickly as they are on Earth. So I actually spent some time Googling all that. And actually, I was taking a course at the time where, one of the signal processing techniques was, in order to isolate something, you take a reference point. So I was thinking, okay, maybe you can use the ice cap on Mars as a reference point. And I started to look in on it, and I found out a couple of things. And one is, the ice caps on Mars are mostly carbon dioxide. They're not water, and they migrate through the atmosphere from north to south, according to the seasons. The other thing is it's got almost no atmosphere, like a fraction of a, pound per inch or whatever it is. And the third is it has no magnetic field, no to speak of. And and I realized at that point, Mars made a very bad reference point. And the other thing I realized is that, Mars is essentially a failed planet because what protects the Earth is the fact that it has a molten core that's rotating and generating a magnetic field, which generates both the inner and outer Van Allen belts. And that protects it against solar radiation and cosmic radiation, things like that, and also protects the Earth's atmosphere from being swept away. And Mars didn't have that. So now out of all the ways that they detect exoplanets, it doesn't appear that they're looking to see whether it has a magnetic field or not, because I think the probability of actually finding a low-level source of life there really would be dependent on whether it has a magnetic field. I mean, obviously in recent years they found extremophiles, bacteria in the Yellowstone thermal springs that can survive. Previously, they didn't think that was possible. They found life forms around hydrothermal events in the ocean, which are very hot. They didn't think that was possible. And as you mentioned, they found, what could be single-celled organisms buried in rock, several meters deep. And so it's kind of interesting they're not looking at the magnetic field of exoplanets, which I think is a crucial indicator.
Well, you brought up a good point. I don't know if you guys remember, but when I was a kid, I remember they used to think that there were canals on Mars because their telescopes weren't that good, because they turned green and then they would go back. And so everybody thought that there was actually canals, and maybe even people living on Mars when I was a kid. So we've come a little ways from that.
Martians.
Martians.
Didier?
Yeah, well, it's in the same line of what you all have said. I think this lecture you gave us really made me realize that the form of life out there doesn't have to be with two legs and two arms and a head and a brain. Those are little particles that thrive with maybe some amino acids. The one thing that surprised me about 25 years ago is the discovery of a Helicobacter. There's a condition called peptic ulcer, and it's a stomach problem caused by a bacteria that is living in the stomach. And the stomach has an extremely acid content, and nobody really thought that a bacteria could thrive in such an environment. But two Australian physicians, and they got the Nobel Prize for that, they discovered that there was indeed a bacteria that you can get that would cause all those problems. And that goes along with what you said, that the environment doesn't have to be oxygen and water. It can be, as Walter said, embedded in a rock, and you said that too. And those organisms do not have to multiply every few days, like the skin cells, but they can take 100 years to multiply. Your lecture has really opened for me a lot of doors, and I thank you very much. This was great.
Thank you. And I've always felt that maybe bacteria is really the true form of life on our planet, and it's just laughing at us as because it's everywhere. I mean, there's 3 pounds of it in every one of our bodies, and
Got
it's just saying, let's see
Got
what these
you.
idiots can do to the planet.
Yeah, you get pneumonia. Got you.
Alberto,
Oh, you gotta.
Alberto, you have to unmute.
Oh,
Alberto, you have to unmute.
who's on?
Alberto,
Okay, me.
not you.
Okay, sorry.
Alberto. Well, you got more, Bob?
I just have one thing I want to mention.
Oh, wait, he's got it. We'll get you next, Bob. Go
Yeah,
ahead.
no, I wanted to compliment what Didier said because in order for life to exist, you have to get a membrane first, right? Otherwise, the electrolytes or the solutes in the cell that are floating in a solvent, in this case could be water, or could be anything else, we do not know. Methane has been also suggested as a solvent for life. All those elements would be lost. And it's very interesting because if you look into the virus, what are the virus actually? They are nucleic acids. And they are contained in a membrane, and that's it. No more than that. And viruses are supposed to be, forever in this planet. One of the most archaic types of life, and they continue striving. So there could be an array of different types of life outside of this planet. I'm convinced of that. And if we have, more opportunities to study them, go to planets that are or moons that were supposed not to be in the golden zone, but now are discovered to have oceans below the surface, we probably can see something there or find something there. So very interesting talk, John. I really enjoyed that stuff.
Thank you, Bob.
Not better.
Yeah. Okay. Just obviously, I'm not. I don't have a scientific background, but I just want to give you some anecdotal things about what I think, and what I think is that one of the things that man does is that he has an incredible ability to predict the future. Think about Jules Verne and the submarine. Think about Flash Gordon, space flights, moon, traveling to the moon, ray guns. Think about Dick Tracy speaking into his watch. Think about Arnold Schwarzenegger in a movie talking about virtual reality. All of these things eventually became true. So how's this one? Every single movie that you see about life, another form of life coming to the United States. I mean, most of the times they have those big heads, skinny bodies, long arms. So maybe what you're seeing in the movies and what man is thinking about, it looks like, is that that's actually real, like all the other stuff, and it'll come true. That's my unscientific comment.
One of the things that a lot of people ask me as was talking about this is, do I think that aliens have visited the Earth? And they were talking about the where these lights and different things show up. my thought about that is that maybe it's not aliens. Maybe somebody in the future discovered a way to go back in the past, and that's how they're visiting us.
Yeah, who knows?
Hopefully to stop us from doing stupid things. Anybody else? Oh, Mitch.
Yeah, hey, I just wanted to mention that as I've been thinking about this off and on, including when we had that talk about the Drake equation here 5, 10 years ago, that, if you think about us and, up until nominally 100 years ago, you know, we couldn't have cared less if aliens were sending radio signals or hyper radio signals or anything else because we just couldn't deal with it. I mean, we just there was we were totally deaf to any kind of things except for them, settling down and popping out of the hatch of their space, their flying saucer. And if you go forward, and I'm just going to pick a random time interval, 10,000 years. By that time, anybody here would not care about what's going on other planets, or would not need to communicate with other planets because we already know what they're doing, and we don't need to bother them. And so there's nominally about a 10,000 year window, and life on Earth has been going for what, 3 billion years or some number like that. So that 10,000 year window starts to look really small. And so, the fact that, hypothetically there are hundreds or thousands of planets out there that have life on them. First of all, they're either way before our current status here, or they're way after our current status here. And so they simply, there's just a small window of time when they would care to communicate with us. So that's just a thought on my part. I can't prove it any more than anything else, but certainly, if there's a bacteria on planet X, they can't communicate with us, and they can't. We may be able to detect they're there by the various molecular signatures. We're starting to get to that point now, but and then on the other side, if the civilization is way farther advanced than we are, why would they care to even bother looking at? I mean, they already know what we're up to. They've got technologies that we can't even think about. So,
Well,
it's a narrow window.
Well, that's what I meant by if they did see our early radio broadcasts, would they want to come here? I mean, remember, some of that stuff was going out was during the World Wars and stuff. And would you want to go to a planet where they mass kill people? Not me.
Or I Love Lucy. Oh my God, let's go to that planet. They have I Love Lucy.
Yeah, they never had sex. They always had two beds.
But you have to consider that if there are billions of planets and they may have life, there may be some planets which are at the state of evolution where we are right now. So there may be some planets where they have a curious creatures about their surroundings. So
that's true, and they may have figured out faster than light communications, and so I mean, who knows? But
yeah,
it just is, the odds of a planet out there being on the same timeline that we're on is pretty darn small.
I'd like to add something on the timeline bit. Our star is our sun is a main sequence star with a projected life of 10 billion years. And so we're at the halfway point, roughly 5 billion years. The age of the universe is around 14 billion years. The early universe was nothing but hydrogen and helium, and you had to get one star to go through its full life cycle to be able to generate the higher elements that we see today. So you're talking about 10 billion years right there. And therefore, by definition, our solar system is at, the most recent one that will have life and have all the higher elements, because it's after the first stars, explode and scatter the remaining elements that you have new solar systems forming. And therefore, there will not be any life form, any sooner than our Earth system. Okay. Now, obviously, the other thing was, the timeline. Humankind has been here only a short years. Civilization's only several thousand years. Technology is only about 100 years old, where anybody could even think about looking elsewhere. So, having an overlap there becomes very small.
Joel, first of all, I'd like to thank you for saving my presentation. But go ahead. What's your question?
Yeah, it's not more a statement. The universe could be teeming with planets, all with life, but the distances are so far that the probability of being able to communicate with one another is next to zero. When you think about the closest star, well, actually, the closest star is 4 light years away, so that's not a big deal. But when you talk about other galaxies, they're hundreds of millions of light years away. So even if you were actively trying to communicate, there's no chance that you're going to be able to get to talk to one another.
Hey, Joel, that's interesting. I read something, maybe you guys could confirm this, but I recently read something that the original probe that was sent out seeking to see if it could communicate with any other planet,
Voyager.
it has traveled 120 million light years. Does that sound right?
No, not
No?
even close.
Okay.
Not even a light year.
Okay.
Yeah.
I think I got that from Chatbox.
Oh, well.
Ask Alexa, she'll tell you.
It's going at something like 40,000 miles an hour or less for
Okay.
40 years. So it's not going very far. It's out of the solar system, but
Okay.
it's not really very far.
Mark?
Yeah, so, we keep mentioning some form of the Drake equation, and it was a wonderful idea. But everybody interprets the Drake equation as a progressive thing, like civilizations will arise and they'll keep getting better and better. And so then the question comes, where is everybody? Why haven't they come to us? But you can also reverse the argument and say that since, no other civilization is visiting us, probably any other civilizations have eventually discovered that it's just not practical, so they can't do it. And we may discover that too, if we last long enough. So it could be that, just as Joel was suggesting, that there could be other civilizations and they're simply separate and they're isolated from each other. And just because they can detect each other, maybe, doesn't mean that they can communicate in two directions. And so that's just another way of interpreting that same equation.
Yeah, Mark, there's a TV movie on that's called The Three Body Problem, and it's also a couple of books, and it speculates that somehow that we contacted almost by accident another civilization. And the amazing thing, it was a pretty amazing movie. What happened is these people couldn't travel at the speed of light, but somehow they could transfer their thoughts into our realm and control things on Earth. to the point where they could cause mass illuminations of the stars and other things. If you get a chance and can see that, I forget which one it's on. It's a fascinating movie about contact with another planet. Science fiction.
Robert, you had your
Science
hand
fiction.
up, but I'm sorry.
It's science fiction. They're at Netflix. And by the way, the two other books are being filmed now, so they will appear in
Oh, great.
2026. Yeah.
I can't wait.
Yeah, that's amazing because it talks about the civilization that as soon as we connected with them, they are coming us to conquer basically Earth, and they will take 450 years to get to the Earth because they already have reached zero point 0.1 of the light velocity. And yeah, it's a very, very creative book, and it contains something that is somehow happening now because it's a Chinese author, and he's talking about the sun in the next books, talking about the sun that is created by China in order to get energy, which is in the vision of Chinese people to create that sort of putting, in the outer space, solar panels, gigantic solar panels, and make them produce energy for distributing to the earth. That's just amazing.
Rick?
Yeah, I'm just playing off what some people have said, but maybe adding to it that as I think about the distances that might exist between us and an exoplanet that has intelligent life, or between one planet, call it planet A, that has intelligent life, and another one, B, that has intelligent life. We may be talking hundreds of millions of years, millions certainly, I think, maybe hundreds of millions, and the disparity between those, where they are in their own evolution and where they're going, or if they've already disappeared, seems to me to say that we really it's a very, very, very rare expectation that we will have meaningful contact with another intelligent life form. I don't know if that's pessimism or optimism.
Yeah, and it bears mentioning that anything we observe that's many light years away is also that many years in the past.
Sure.
And so if you observe something that's 100 million light years away, it's 100 million years in the past. And so if you could go there, you might not find much.
Yeah, but one of the things you got to think about is how many people thought that we'd carry around a computer in our pocket, or more importantly, when you were kids, how many people thought that we'd actually go to the moon? So maybe we're just stuck in this thinking there's channels on Mars, and we can't get away from that.
Hey, John, that was Flash Gordon. I mean, I watched it as a kid. Space rockets going out to outer space, to the moon. I mean, that was the big thing with sci-fi back then. I remember watching on my 8-inch Dumont TV.
Yeah, that was a rocket ship with a sparkler in the back.
Right.
Yeah.
Does anyone else have a question?
I sent a chat thing out just for thought for another day.
Okay. Well, I'd like to thank our speaker. This turned out to be a great presentation with lots of questions, a lot of participation by the group. And I'd like to give John an all God salute.
Absolutely.